Hello students, welcome to EPG Pathshala. I am Dr. Varun Vyas from Department of Physics and Astrophysics from University of Delhi. Today we are going to talk on module resistivity theory under the paper Characterization of Materials Part 1. After completing the module, a student will be able to understand the Drude model, semiconductors and insulators, and superconductivity. The electrical properties of semiconductors can be understood after having the adequate knowledge of density carriers. The net flow of both electrons and holes generate currents in a semiconductors. Energy is transported by electrons, holes, photons, excitons, and other particles. Precise knowledge of the of motion and the scattering of electrons is necessary to understand the conductivity of the material. In-depth studies of electrical conductivity of solids shows that a totally perfect solid can exhibit totally unexpected behavior. Owing to the random nature of the scattering of electrons after their collision within the lattice, the velocity and displacement of given electron averaged over a long period of time, considered as a resultant vectors, should be equal to 0. Being randomly distributed, the mean displacement of the electron is 0, and to establish a current, a directional motion of electron is needed. Such random motion cannot result in an electrical current, which describes the transport of charge across some cross section. After the discovery of electron in 1897 by J. Thomson, the Paul Drude and Hendrik Anton Lorentz proposed a classical theory to describe the electrical properties of metals on the basis of electron gas model. The proposed classical theory didn't prove to be accurate because it doesn't consider the quantum effects, and also it neglects the long-range interactions between the electrons and ions. But qualitatively, it works surprisingly well. This section shows how Drude model describes the electrical resistivity of metals. Drude model consists of a metal of valency Z as a lattice of positive ion cores and a gas comprising free electrons moving around those cores. Each atom donates Z electrons to the gases. This electron gas acts like an ideal gas, where the electrons randomly move at high speed, while also colliding with the ionic cores. Drude model does not consider the long-range interaction of electrons with other electrons or ions. For understanding the electrical current phenomena and resistivity via Drude model, several collective properties of electron gas are needed. First, let us consider the electron density. Ne is equals to number of electrons per volume. This is given as equation 1. For a metal having density ρm is equals to mass by volume, atomic weight is mu, and valency is Z. Ne is equals to Z into n atoms. This is equals to Z into ρm into mu by Na. This is represented as equation 2. Here, Na is equals to 6.02 into 10 raised to power 23 atoms per mole. This is equals to 6.02 into 10 raised to power 26 atoms per kilomole. Equation 2 can be used to determine the electron density of a given metal. For instance, copper with rho m equals to 8960 kg per meter cube, mu is equals to 63.55 kg per kilomole, and Z is equals to 1 in metallic form, has the electron density of Ne is equals to 1 electron per atom multiplied by 8960 kg per meter cube in brackets 63.55 kg per kilomole. This is divided by 6.02 into 10 raised to power 26 atoms per kilomole. This is equals to 8.49 into 10 raised to power 28 electrons per meter cube. This is represented as equation 3. The drift velocity can be defined as the average velocity vector of an electron under the influence of external applied electric field, and can be expressed as drift velocity is equals to 1 by 9 multiplied by sigma of Vi. This is represented as equation 4. Owing to the fact that electrons exhibit random motion, the drift velocity comes out to be much smaller than the average speed of an electron. This is represented as average velocity is equals to square root of v square is equals to square root of 1 by n into sigma of vi square. This is represented as equation 5. Likewise, the average velocity vector of an air molecule represents the wind velocity. For air, average velocity of the molecules is equals to velocity of the wind. This is given by equation 6. Whereas the average speed of air molecule because of the thermal motion is calculated as square root of average velocity of the molecules is equals to square root of 3k into T divided by m, that is molecule, is equivalent to 500 meter per second. This is represented as equation 7, which is much faster than any wind. However, this difference is much larger for an electron gas at room temperature. The average speed of an electron while moving thermally is given by average velocity is equals to square root of 3 kt divided by me. This is equivalent to 120,000 meter per second. This is represented as equation 8, whereas the drift velocity of an electron is typically of the order of few millimeters per second. The electric current density can be determined from the drift velocity Vd and the electron density Ne as given below. J is equals to minus E into Ne into Vd. This is represented as equation 9. Here E is the charge of an electron. For instance, drift velocity Vd is equals to 1.0 millimeter per second in copper, with Ne is equals to 8.5 into 10 raised to power 28 per meter cube, has current density of J is equals to in brackets minus 1.6 into 10 raised to power minus 19 coulomb into brackets 1.0 into 10 raised to power minus 3 meter per seconds into brackets 8.5 into 1028 per meter cube. This is equivalent to minus 14 into 10 raised to power 6 ampere per second. This is represented as equation 10. Therefore, a wire with cross-section A is equals to 1 millimeter square carries the current I is equals to minus 14 ampere. Here, the negative sign implies the opposite direction of the current to the drift velocity of electron gas. For equation 9, let us consider the electron gas is moving with the drift velocity Vd along a wire of cross-sectional area A. The gas travels through the distance L is equals to Vd into delta T in the time interval of delta T. As a result, the volume of gas traveling through the given cross-section of the wire during this time is given by V is equals to L into A. This is equals to Vd into delta T into A. This is represented as equation 11. This volume has N is equals to V into Ne electrons, and the net charge is given by delta Q is equals to minus E into N is equals to minus E into Ne into V. This is equals to minus E into Ne into Vd. This is multiplied by A and delta T. This is represented as equation 12. Thus, the electric current is obtained as I is equals to delta Q divided by delta T. This is equals to minus E into Ne into Vd. This is multiplied by A. This is represented as equation 13. And the current density is given by J is equals to I by A. This is equals to minus E into Ne into Vd. This is represented as equation 14. Another parameter is the mean free time, tau, in brackets, which is the time during which electron travels freely between successive collisions. The Drude model assumes this time to be independent of the velocity or position of the electrons. Another assumption is that the direction of motion of electron is completely changed when it collides with an ion. As a result, immediately after collision, the electron comes at momentarily rest. When no external field is applied, the force acting on the electron between successive collision events is zero. Therefore, the velocity of an electron does not change until the next collision. However, when an electric field is applied, each electron experiences a force F is equals to minus E into E. This in between collision. This force accelerates the electrons, and this acceleration is given by A is equals to minus E by me into capital E. The capital E here is the EMF. Thus, at time delta t after the last collision is given by V into brackets ith electron is equals to V naught into ith electron plus A into delta t. This is represented by equation 16. Taking average of all electron yields, the net average velocity is equivalent to the average velocity, primary average velocity of electrons plus A into delta t. This is equals to 0 plus A into tau. This is represented as equation 17. The drift velocity in the presence of applied field E is Vd is equals to A into tau. This is equals to minus E into tau by me multiplied by capital E, that is EMF. Alternatively, equation 18 can also be obtained by considering the impact of collisions on the net momentum of n electrons, where P is equals to sigma of me into Vi. This is equals to n into me into Vd. This is represented as equation 19. In very short time, delta t, that is much smaller than tau, is given by n col, that is collision, is equals to n into delta t by tau of the electrons will collide with the ions. On an average, the momentum vector of an electron immediately after a collision is zero, thereby reducing the net momentum p by minus delta p col is equals to n col divided by n into p. This is equals to delta t by tau into p. This is represented as equation 20. At the same time, each electron experiences the electrostatic force F is equals to minus E into capital E, which further increases the net momentum by delta PE is equals to N into delta T into F. This is equals to minus N into delta T into E into capital E. This is represented as equation 21. Thus, the two effects change the net momentum at an effective rate of delta P net divided by delta T is equals to minus P by tau minus N into E into capital E. This is represented by equation 22. For steady current, there should not be any change in the net electron momentum with time. Delta P net is equals to 0, implying that minus P by tau minus N into E into capital E is equals to 0. This is represented as equation 23. In the light of equation 19, this means minus N into Me by Vd divided by tau minus N into E into capital E is equals to 0. This is represented as equation 24. Thus, the diff velocity is equals to minus E into tau divided by Me. All of it is multiplied by E, capital E. This is represented as equation 25. In accordance with equation 18. Finally, on combining equation 9 for the drift velocity of electron gas and equation 11 for the current density, J is equals to minus E into Ne into Vd. This is equals to plus E square into Ne into tau divided by Me into capital E. This is represented as equation 26. Comparing this formula with the standard Ohm's law, J is equals to sigma into capital E is represented as equation 27. Thus, the electrical conductivity is obtained is equivalent to 0 is equivalent to E square into Ne divided by tau into Me. This is represented as equation 28, and resistivity is given by rho is equals to Me divided by Ne square into Ne into tau. This is represented as equation 29. Basic assumptions of Drude model. First, in the absence of an external field, electrons move in a straight line between successive collisions. The effects of interaction of electrons with other electrons as well as ions is neglected. Second, the mean free time between collisions is tau, that is the probability of collisions per unit time is 1 by tau and the probability of having a collision in infinitesimal small time interval, that is dt, is given by dt by tau that does not depend on the position and velocity of electrons. And finally, number 3, we have an electrons achieve thermal equilibrium after collisions with the lattice. After collision, they move into random directions with speed depending on the temperature of the region where collisions occurred. Eventually, the hotter regions, the higher is the speed of the emerging electrons. Applications. This model can be used to distinguish between metals and insulators, determine electrical transport in metals, determine thermal conductivity of metals. Electrical resistivity or resistance represents the intrinsic property of a material and shows how efficiently the material obstructs the passage of electron current through it. Lower resistivity values cause electrical current easily pass through the material. It is represented by letter rho and has SI unit ohm meter. The reciprocal of electrical resistivity is called electrical conductivity, which measures the material's capacity towards conducting electric current. It is represented by sigma and has SI unit as Siemens per meter. In resistors and conductors made up of single metal and having uniform cross-section, there exists a uniform electric current, and their resistivity defined as R is equals to rho into L divided by A, where R, L, and A represent the respective electrical resistance, length, cross-sectional area of a uniform piece of metal. Quantum mechanics provide that electrons within the atom or crystals can only occupy discrete energy levels. The energy values between these discrete levels are not possible. They are called the allowed energy levels. When a large number of energy levels are available, the gap between them is very minute, and these levels can be collectively described as an energy band. Depending on the atomic number of electrons, and their distribution of a material, multiply energy bands may be present in it. Electrons occupy lowest available energy states to attain the state of minimum energy. However, Pauli's exclusion restricts the filling of one state by more than 2 electrons. Therefore, the electrons populate the band structure starting from the bottom. The highest occupied level is known as the Fermi level, and its position with respect to the band structure is significant for electronic conduction. Electrons present in the energy levels lying close to the Fermi level are free to take part in the conduction process, as they readily hop among the partially filled states in the region, whereas the electrons occupying the lowest lying states are tightly bound to them, and the higher states are vacant at all times. Thus, they do not play any significant role to electrical conduction. In metals, several energy levels are present close to the Fermi level, which can contribute to the conduction, leading to high electronic conductivity in metals. A significant outcome of the band theory in the presence of forbidden bands, often termed as band gap in energy or the energy intervals that are devoid of energy levels. In insulators and semiconductors, the electrons fill the low energy bands up to the boundary, and Fermi level lies in the band gap, owing to the lack of available states near Fermi level and free movement of electrons. Electrical conductivity is poor. The atoms in the lattice of a metal have readily detachable outer shell electrons, which travel the lattice after dissociating from the parent atom, thereby forming a sea of free moving electrons, resulting in the flow of current. The application of a potential difference voltage across the metal establishes an electric field which drifts the electron towards the positive terminal. Actual drift of electrons is slow, in order of a meter per hour. However, owing to the dense packing of electrons within material, electromagnetic waves travel nearly at the speed of light. The resistance in the metals can be understood by a simple model, where electrons as well as the crystal lattice both are replaced with wave-like structures. While traveling through the lattice, electrons' wave interferes with the lattice wave, thereby encountering resistance to travel. Higher regularities in the lattice, lower is the resistance. Magnitude of this resistance is determined by two factors: A. Temperature and vibration speed of the lattice, and B. Impurities in the metal. Larger cross-sectional areas result in the more electrons per unit of length available for current conduction. Thus, thicker conductors exhibit lower resistance. Similarly, larger the length traversed by the electron to reach the other terminal of the conductor, more the number of scattering encountered. Hence, the resistance of the conductor increases with increasing length of the conductor. Semiconductors and insulators. Fermi level is present in the conduction band of metals, resulting in easy availability of free electrons for current conduction, whereas the Fermi level lies in the middle of the conduction band minimum and the valence band maximum in case of undoped or intrinsic semiconductor. Consequently, at absolute zero, that is 0K, there are no free electrons available, and the conduction is zero, resulting in infinite resistance. The resistance decreases with the corresponding increase in charge carrier density inside the conduction band. Doping results in the creation of excess electrons inside the conduction band or holes within the valence band, resulting in increased concentration of majority charge carriers. Doping can be either donor or acceptor atoms. Both type of doping can cause reduction in the resistance by increasing the carrier concentrations. Thus, heavily doped intrinsic, heavily doped extrinsic semiconductors essentially behave as metals. At elevated temperatures, thermally generated carriers from the dominant part of overall carrier concentration. Therefore, thermally generated carriers dominate the conduction process at very high temperatures, and resistance decreases exponentially with increasing temperature. Ionic liquids and electrolytes. In electrolytes, the electrical conduction is due to ionic movement and not by electrons or holes. Thus, electric charge is transported by moving ions. The resistivity of an ionic solution or electrolyte varies significantly with concentration. Consequently, distilled water acts as an insulator, while salt water conducts the electricity reasonably well. Electrical conduction is ionic liquid is also determined by ionic movements. However, here the molten salts travel and not the solvated ions. Ionic salts conduct current in biological membranes. Ionic channels, that is pores, present in the cell membrane are selectively permeable for certain ions, thereby deciding the resistance of the membrane. So students, let us now summarize what we have learned in this module. In this module of resistivity theory, we studied about the Drude model, which considers a metal as a lattice of positive ion cores and a gas comprising free electrons moving around those cores. Next, we briefly discussed about semiconductors and insulators, followed by ionic liquids and electrolytes. And in the end, with superconductivity and decrease in resistivity of metals was also discussed in brief. Thank you.